yet. These typically are around 4 gigabytes. We render them down to save space to about maybe 750 megs or almost a gig. There'll be a YouTube site where these will reside at, okay? At the end of each week, or as quick as I can, it takes a little while to render it down, but it's a lot of information. I mean, a lot of data, okay? A lot of SRAM, as they say. You're going to need your computer up. Yeah. All right, let's do a quick test. Just hit A, B, C, or D, just to make sure this is up and... Hit any button. All right, we're good. Okay. A what? I have 30 of them. I'll have to get some more. But share it with a friend. Click once and then share it with a friend, and then you can click again. Oh.
There's no way too, because you're not going to get a model of signals in MATLAB unless you're like unless you made MATLAB.
All right, should be warming up here. All right, cool. All right, so everybody got their... I don't have my screen. Screen was on, now it goes off. Ah, come on.
I couldn't get E now. I mean, I couldn't get E on MATLAB.
Come on, screen. All right, here we go again. This projector, something's been up with this thing. It stays muted. Like I just had it on, and then the whole thing just shut off. Yeah, I mean, it just shut off. I mean, it's on. I had it on. All right, well, I'll let you take a look.
It's obviously not muted at the moment. It doesn't even appear.
There it goes. Now, then it just shut off. There it is. It just
went
blank. All right, leave it. We're good. Thank you. Yeah, for now. Don't run away on me. All right, so I guess in lab yesterday you all had your butterfly board and you soldered. Did you solder the There, and you soldered your date tag. All right. And then you tested the speaker, right? I'll go over some of that code on Friday of how that actually works. Did Sun go over how actually that code works? Did you change the frequencies? Okay, all right, because you're pulse width modulating that thing, all right? So you're sending out different tones. Okay, thank you, Brock. All right, good. So, I mean, we're going to be getting into hardware soon. So, all right. Somebody sent me a question on Chapter 2. Tyler? Is Tyler here? Where you at, Tyler? All right. What was the...
One was, how do you know if an ADR chip has an EEPROM or if it does or without EEPROM?
You have to have... There's two EEPROM. Let me go back here. All right. This flash is EEPROM. You have to have it because you have to be able to program something in. That's one. Now hold, time out. There's another EEPROM over here too. All right. So what this EEPROM is for is to burn in data. If you have parameters like for a, let's say it's for an exercise machine or it could be for a car or something, they will burn in parameters specific to that engine in here. So you don't have to keep writing it here, okay? Now, let's make sure that we understand something. It says read-only memory. Is it really read-only memory? No, because you write to it. Usually, once you finally write to it, you kind of leave it alone unless you're going to keep rewriting. I mean, once you basically make an application-specific, circuit, once it's done, then you ship it. And then you really don't play with it again until, like, your engine control modules. I had an issue with my car the other day. I thought that they would have to reflash that thing, all right? But typically, when you're in production and sending it out, that gets written to, and then that's where the program resides, and then all your data parameters sit down in here. Okay? Does that answer your question? All right. And you have SRAM here too. All right. So, but that's non-volatile. When you shut it down, it goes down. There was two parts to your question.
Yeah, and is the address range for chips
All different.
are they specified in like somewhere on Blackboard? Do we have that, like the 169P?
Yeah, that's in the reference manual. Go to the reference manual under. I don't have my Blackboard up. Let me just get the TU Portal real quick. It's also in the slides too for the 169P. All right, if you go to content and then Atmel manuals and tutorials, 169P manual. And we're going to go to AVR memories right on 7. And there it is right there, okay? And if you do this, if you go to the Atmel, like we're going to run some code for the 2560 today, this goes all the way down to FFFF, all right? FFFFU, all right? Or whatever, all right?
They don't show you like the GPRs.
All of them have, every Atmel processor has the GPRs, 32 of them. Every single one has it. That's built in. Those 32 general purpose registers are in every one. And there's a reason why they did that. I mean, usually in the past, you would do a lot of operations on what's called a stack to move things in and out. The stack is a special memory, whatever. They extended this register range so that you can do it a lot easier with these general purpose registers, okay? There's a lot behind the scenes. And what we're learning here, I mean, when we're talking about memory and this kind of stuff, you're learning firmware. You've heard of software, right? You've heard of hardware. The firmware is the stuff that goes between, and that's exactly what we're doing. With these opcodes and all this stuff, we're taking something on a high level. I mean, I even think of assembly language as a high-level language, but it's really not. But you're actually, the interaction of hardware with the software, we're doing firmware. I mean, that's what we're doing. Somebody had a hand up?
How do you load a value in the registers 1 through 15? You don't know.
No, you have to go into 16 and then go, well, no. I will show you how there's a way you can cheat and load it in.
Because you can add like a 1 in a...
Well, I'm very, this is a very important point that he brought up, and we're going to talk about this in depth right now, all right? Why can't you load in R0 through R15? Okay? So, I mean, Tyler, okay? 7, yeah. So this is if you're going to go to a 2560 or the Atmega 32, I would advise you, again, the book uses the Atmega 32. Grab that manual. Every now and then, I mean, I used to use the 2560. Some of my slides have that on there. This stuff changes, okay? And the length of the special function registers, that changes because if you have more I/O and stuff, it's just that's going to change, all right? So what I'm saying is this is the 169p. This is it, all right? That is it. You got 64. You've got this other extended stuff. This number, these numbers are going to be fixed for every processor. Every Atmel through 1F is where the general purpose registers go. Every single one of them, that's where you got your 32 registers at. This in here will vary based upon the chip because it depends on what the functionality is. What special, that's why we call it special function registers. What special functions do you have built into that chip, okay? And then the RAM will go up to 04FF. I'm going to show you where you can make a mistake with this, and I can write right into here. So your question about writing into R0, you can do it. You got to be real careful about how you do it, all right? So we'll get to that. That's a very good point. They reserve R16 through R31 to do a lot, you go into R16 through R31, and then you write into R0 through R15. All right, so let me get it forward here. All right, so let me start right here. Let me make sure I got everything. Good. All right, we're all set. All right, a couple of things. How many bit is this microcontroller? 8-bit. All right, why? Why is it 8-bit? The data bus, that is it. If you notice over here, again, here's my program flash, here's SRAM. This is 16 bits wide, this is 8 bits wide, all right? The reason we call it 8-bit is due to that number right there, all right? It's the length of the data bus. If you notice, there is a, the whole key about the Harvard architecture versus the von Neumann architecture is the von Neumann architecture, you have one address bus, one data bus, one control bus. In the Harvard architecture, this bus is separate from this bus. The wiring is now you've doubled up the buses. What that allows you to do is I can grab stuff from program flash, all right, without clogging up anything on the other side over here. So that's a key difference. We don't call it a 16-bit because that is 16 bits. It's because it's whenever they talk about 32-bit, it's your data bus. That's the size of the data bus. Now, the nice thing about having a 16-bit quasi-flash data bus over here is how our instructions are how many bits long. The instructions, the opcodes and all the instructions. 16 bits. They take up one memory location. Some of them may take up 2. So they take up 2 words or 16 bits. All right? 2 words or 16 bits. Now, the nice thing about it is I have an instruction in here. I can read that instruction out, get it into the instruction decoder in one cycle of the clock. That's the beauty. That makes it really fast. Remember, flash memory is a slow write process, but a fast read. So I'm reading it really fast. Okay? All right. Let's see. So again, 16-bit, 8-bit over there. All right? And again, the main difference between the von Neumann and the Harvard architecture is you've got separate buses. All right? So these buses are separate from those buses over there. I don't know why it keeps repeating itself. But okay. Your question, my friend, is LDRDK. We're just going to load immediately a value into a register, okay, into one of these 32-bit registers. The question is, why do I have to start here and going down here before I can start writing in here? All right? So these are just loading immediates. Okay, here's where it comes down to. The actual 16-bit instruction that's going to go into flash for any LDRDK is going to have an E in front. The K and this K, again, I can load how many bits can go into any of the general purpose registers? How many bits? 8. So in hex, where does it go from? 0 to FF. So it goes from 0 to 255. So the numbers that I'm loading in, this K, when I load in, this is K here, this is the hex number. This can go from 0, 0 to FF. Part of this number is going to go here. The other part of this number is going to go here. E, that's the hex for E. E is the LDI. So every load immediate instruction has an E for the opcode. All right? The question is, what is this D over here? If you notice, we got 16 through 31. You were asking me about why. Register R16 through R31 is this LDI-R. There's the little D. And there's your D's in here. That's affiliated with this. All right. So I'm going to call 4, I don't call it, everybody calls it. 4 bits are a nibble, all right? We have a 4-bit here, which is nibble 3. This is the most significant byte on the left, the least significant bytes on the right, or bit. So I have nibble 3, nibble 2, nibble 1, and nibble 0. The first nibble here is always for the opcode of the instruction, okay? That's always going to be there. So that's the key. So the opcode you're going to see for all the LDIs are going to have an E in here. All right, they're going to vary. If I do an add instruction, subtract instruction, a negate, whatever, that opcode's going to change. I mean, because you've got a different instruction. All right, these two, the second and the 0th nibble, are for the 8-bit. This is the 8-bit number. K is an 8-bit number. Hex data that gets loaded in a register. I'm going to load in. Now, again, this is the way Atmel decided to do it. I don't decide to do it. They break it up into the lower order nibble. In our case, 0 is going to go in here. So this will be 0, 0, 0, 0. The 1 will go 0, 0, 0, 1 in there for this one. All right. This one. This nibble answers your question. This corresponds to a register number, and note that 16 is less than D, which is less than 31. Notice that this is 4 bits, right? 4 bits. And I'm going to load in a register that's going to start from 16. So we've got R16 through R31. Now, the number 16, convert that to binary. What is it? How many bits is it? How the heck is it going to fit in there? How's it going to fit in there? You get rid of the most significant bit. We're going to drop off. They drop this off. So 16 is this. All right, so 16 base 10 is equal to that base 2. 17 base 10 is equal to 10001. 18 base 10 is... So now what you're going to see, if I load in, well, we'll get to it in a second. All right, so again, the opcode is the 4 bits, gets loaded into the leftmost nibble. Now we break it up, bits 15 through 12, 11 through 8, 7 through 4, 3 through 0, all right? So for the LDI instruction, it's a 16-bit word. We now have this 1110 is that guy. So that takes care of that. Now we're going to look at this one, which I'm talking about over here. There's your nibbles, there's your bits. All right, once the opcode is determined, the operands must be coded. So now we're working on the operands. The destination register is specified by 4 bits occupying a left nibble, the second byte, bits 7 through 4, right in here. Then we're going to have the destination field is 4 bits, and that's denoted by DDDD. The LDI instruction can only access 16 different registers, and it's restricted to R16 through R31. When the LDI instruction is decoded, the leading one is added to the 4th bits representing the destination register to make it a 5-bit binary number. So for the LDI instruction, these bits are this guy, okay? So again, there's my nibbles, there's my bits. So now what we do, you got the leading one is going to be added at the decoding process. So now we've got this 4-bit number. We strip off that leading one to determine the contents of the field and the destination register. So therefore, that leading one that we had over here, this one right there gets dropped to the 0. So the R16 is going to have 0, 0, 0, 0 in it right there. All right? So now, if I did an LDI R17, comma, 0, that, some of these pens are dying on me here. So if I do an LDI R1701, here I've got my 16 bits. I'm going to have 1110. That's the opcode for LDI. Then I'm going to have the 0 is going to come in here as 0000. R17. All right, this 1 is going to come in here as 0001. What's going to go in here? 0001. Which corresponds to that. That makes sense? Yeah.
Is this set up only for the 169 bit?
No, it's for all of them. All of them. This is the instruction set. When we're doing this, these instructions are across. Again, it would be crazy to make it different for each processor because now there's no consistency across the architecture.
But all these processors are 16 bit.
No, wait a minute. 16-bit, 8-bit. What are we talking about? The instructions are all 16-bit.
This instruction is going to data bus?
The instructions are coming. Go back. Here. They're coming out of here. All this stuff that we're talking about here, this is sitting all up in here. And that's the same for all the atmos.
Is LDI always 1110?
It's the LDI is the opcodes for that are always E. Always. Always. Yeah.
So if the instruction changes from LDI to something else, then the output changes?
That's going to change. It has to. It has to. Yeah, and we'll see that. I'll show you that. All right. The reason I'm doing this again is I'm trying to show you what's happening from a software point of view, LDI, to what's physically happening in the hardware. And what do we call it? underwear. Hanes, Fruit of the Loom, whatever. You know. Once you get under the underwear, sorry, you're naked. All right? But that's what it is. We're getting down to, you can't get any lower than this. All right? It just doesn't happen. All right? Somebody had a question? Yeah.
The data bus from the flash to the CPU, that's not bi-directional, right? It's one, you can only go from flash.
Yes, that would be one directional because it's read only.
So then how we get like data into PROM is what we actually type in on the computer?
Yeah.
That's what goes into the flash?
That's what goes in the flash. Yeah. I shouldn't say it's read only because you can write to it. Because that's where the program has to get written.
But the CPU can't write to it.
No, it's going to read from it. That's the program counter sets up where I'm going to read, where am I on that 16-bit by 8K of flash for the 169p. Okay, so we okay so far? Please don't hesitate to ask questions. All right, so there's the leading one. So the LDI, there we go. The K and the K, those are going to be what the since we're going to load in this 0, 1. Now again, this could be 0, 1, A, E, F, F, whatever, as long as it's an 8-bit number. That just gets broken up into the 0 and the 1 are going to get inserted into 2 and 0. So the zeros are going to go in here for that, and the 1s are going to go in here for that. So therefore, in the end, the opcode for this instruction has E001. And it's going to change. If I change that number up there, it's going to change. So here's the one for LDI 25's 3C. What we do is we say, okay, well, I know I have an E here because I'm doing an LDI. That goes there. The question is, here is the 3. The 3 there gets put into here. The C there gets put into there. You take 25. 25 to get 25. There's 25 decimal. Here's 25 binary. Drop off the leading 1. Put it in there. And there's your full instruction. That's the opcode for the full instruction.
You just think about it as just minusing 16, subtracting 16.
Any way you want, man. You're awake today. Good stuff. No smoky smoke last night? Or? No? Okay. All right. Good stuff. Makes you drowsy. If you go back and look, all right, don't worry. You think this is tea? This is vodka up here. No, just kidding. This is green tea. No. No. All right. If you go back and look, when we did we were doing loading R17 with 0A3, loading R18 with the number 4. And if you go to that website that I showed you, you bring up all the opcodes. Notice that all these instructions, what do they have? What are they doing? Loading immediately. And if you notice, what's the first thing over here? EA0. If you notice, this is for loading A0. All right? So here I have an A. All these are going to be A. So if you notice, I have the EA, because I'm loading A, and I can go from 0 all the way up to what? F. And that's how this table goes. It goes all the way up to F. So the opcodes are, basically the only number that's changing is this number, because we've got EA0, and then I'm just going to change this thing all along here. All right? So everybody got it? All right, good. Now it's time for the clicker quiz. LDI R2703B. Give me an A, B, C, or D. What's the proper answer? A, E3B3, F43B, EB3B, or E3BB? Let me try to shrink this down a little bit. We're getting a run on D. Everybody's changing their mind. Don't change your mind. I got a lot of wrong answers here. All right, so we got LDI. Let's go over to here. We're doing LDI, R27. This is a 2.7, and what are we loading in? 3B. All right. We have E. E is good. All right, so it's got to be an E. It can't be the F. All right, so it cannot be this guy, because that's not an LDI. All right? All right, so now we're going to take this out, and this out. So 27. All right, let's start off with the 3. The 3 is going to go in here. So there's 3. So it's going to be 0, 0, 1, 1. So that's 3. The B is going to go in here. What's B? 1, 1, 1, 0, 1, right? Isn't that B? No? Oh, no, wait a minute. 1, 0, 1, 0. Yeah, I'm sorry. 1, 0, 1, 1. All right, now, the question is, what goes in here? We got 27 decimal. What's that in binary? 1, 1, 0, 1, 1. Let's drop off the leading bit. So what am I left with? 1, 0, 1, 1, which is equal to B. So B goes in here, so I'm going to have 1, 0, 1, 1. All right, so the answer is D. Okay? All right? So over here, just remember, take a look. It's got to be an E. It's got to have a 3 in it, and it's got to have a B in it. The only thing you're looking for is what that list, this guy is in here. Okay? But with me? All right. All right. I didn't answer your question yet. But no, do you see where we're going here? They force you to use R16 through R31. Okay? Questions in the back? You guys all right? Okay. All right, so here's what's happening here. Here's a program. Basically what we're going to do is we're just going to load up R16 with a 1 in it, add R16 to itself. Okay? Here's what we have. Flash, instruction register, instruction decoder. Out of the instruction decoder, this is the finite state machine part. You had this back in digital. A processor is made of 2 things. What are they? Okay, CPU is made up of what? Yeah, all right. What's in the ALU? You got registers. You got. All right. Okay. Be still my beating heart. How do I control what's going on in the registers as far as reading and writing? Where's that come from? The instruction. These control signals. This is a finite state machine, remember. What's a finite state machine made of? Flippy floppies? Right? Yeah. This is what we call academic retention. A lot of partying over the summer kills the neurons. Forget what the finite state machine's doing up here. Okay? None. You've got these control signals. Now again, this CPU is comprised of a finite state machine, and what do we have over here? Register, RTL. Didn't we talk about RTL in digital? Register transfer level? You had to have. You talked about registers, right? And you did RTL. All right. So I've got flash here, program counter, address calculation, 32 registers, ALU, data bus, other I/O out there. All right. So when this is kind of crazy, but I should have written it this way. This is the opcode for R1601. This is the opcode for adding R16 to 01. Notice the opcode for add is 0F00. That's just for adding R16 to itself. All right, so here's what happens. You take the E001, goes down the instruction register, gets put into the instruction decoder. The 01 comes out through the ALU. There's no addition going on, but it has to go through this route, comes back up, and it gets loaded into there. As that's going on, again, it's a pipelined architecture. You're grabbing the next instruction as this one is getting decoded. So the 0F00, which is the add R16, R16 comes in. Once this one gets decoded, I now take the one side of R16 comes down to the one side of the arithmetic logic unit. The 1 comes down to the other side. You add them together. That gives me a 2. That then gets put back into R16. Because the way this add works is these operands, it's whatever it gets added to, it's going to get put into this left one right there. Here's your instructions. We will get to, now if you notice in here, we talked about the loading. There's load directly to memory, load indirectly. We'll get to this stuff. The X, Y, and Z registers, they're comprised of R26, 7 is X, R27, no. I'll get to it. All right, we did this. We added. If you need to add some numbers, that's that. All right, I want to get to, we did, I think we ran this the other day, didn't we? I'm going to still get, I didn't answer your question yet. I'll show you how to get to it. Let me get to it. Hold on. Hold on, let me get back here. All right, this one we set up a sum to be 300. We organized everything at 0, and then we just did some additions, and we stored the sum in location 300, okay? In location 300. Now, the thing about it is we stored it down here. Let's go to, I'm going to go a few slides up. Here we go, right? And I want to jump a little further up. There. All right, I forget. Slide number 59. Grab that code. And bring it into here. What we're doing is we're just going to store some numbers into SRAM, all right? Now, pick your poison up here as far as what processor. I want you to first pick up here, pick the 2560, all right? Then pick your simulation tool. Then do a build. And then we're going to single step through it. Change your flash down here to IRAM. And then change this address from 0200 to 10 to 1000. Okay? What's the matter, Miles? You ain't got no nothing up there, huh? You didn't log in. All right. Log in. Watch what he's doing. All right. Oh, wait a minute. Woo! I put him in the wrong spot. I'm sorry. Don't go to 1000. Go to 01. 01. And here you'll see the numbers, okay? So we went to, we basically had stored R17, which is the A3. What happened here? Oh, I rewrote it. Okay. Did I change something here? All right, load it up, store our, oh, I rewrote, okay, all right. The 4.5, the A3, why is that a 1? You're not getting what?
That one only got 45 and 83.
What did I do here? Did I do something goofy? Well, here, I can single step it.
0100, 0101.
Yeah.
Like ours has that too. If you go up one,
Oh,
yeah.
where are you at here? Let me see.
So like, here's 0101, and I'm assuming this location 0100, which is what you're at.
Yeah.
There's a 1 there.
Yeah.
So it's like the same thing. So
Yeah.
the second column is address 0101, which is what you told
That's
us to go to.
right. Okay. All right. Now, what I want you to do is what we're going to do now is we're going to basically take.
Yeah, I have A3 at that location, the first.
A3? Where?
Oh, at 0100, I've got A3, 45, A2. I think my code's identical, so. I'm at 0100.
Let me go back and rebuild this. What's that?
I'm on the wrong device.
Oh, you're on the 169p?
Yeah.
Yeah. So you can see it highlighted in red. Go up. Yeah. Make this, instead of that, make it 1,000. 10. Make this one, make all these 10s. And then rebuild it. And then we're going to go over here to 10. All right, so now we're writing up in the higher part of memory. There goes the A3. All right, at 1,000. There goes the 4, 5, and there goes the A3 in there. All right, now go up here. We're going to stop debugging. Change the processor. Change the device. So you just click on the 2560. You'll see a change device come up. Change the device. And we're going to put in here 169. And then we're going to go back, rebuild it, and then start single stepping through it. Now again, notice that we're still down here at 1000. Okay? Be careful here. Be real careful. SRAM for the 169p. Zero 04 FF, right? Is it 01 or 04? 04 FF, I think. Yeah. All right, here's the deal. You see this? Run it on the 169p, single step. Notice no numbers are going in here. Nothing's going in there. Why? You're trying to write to the 169p outside of its SRAM because it's only 1K in length. This is 1K. If you now go in SRAM, over here, change that 1 to a 0, and look at what you got. A3, 4, 5, A3. hold on. This answers your question at the beginning. Why can't I write to R0? In SRAM, there's where my 32-bit registers are, right? 0, 0 up to 1F. If you notice, what was down here at 0, 0 is R0. If you go over here on your registers, take a look over here and look at R0. What's in there? A3. What's in R1? What's in R2? You've just written into R0, R1, and R2 without even knowing it. How did it get there? All we did was change the processors. Rachel?
Obviously, it like drops like one of the it's like not enough address spaces.
The address lines, you don't, again, how many address lines are we assuming that we have here? How many bits? 16. On the 169P, it doesn't do 16-bit addressing. Now, it's not 8-bit. Is that 8 bits would be that. So what it did was it looked at these 3 ones here, and what did it do? It dropped them. So where is it writing to? Memory location? 0, 1, and 2. 0, 1, and 2. Which happened to be store into SRAM. STS is store into SRAM. Because that's what we're doing. We're storing answer your question, we're writing over here, which happens to be there. It's 8-bit, yeah. But the thing is, this SRAM varies for the processor that you have. And also that length varies too. All right?
So, can you load immediately into register 0 if you put R0, 0, 0?
Try it. That's what beautiful. Try it. Try it. You'll get an error. You'll get an error.